with vector spaces? Why are we working with modules? And the answer to that is, if you can do it without any extra cost, it's better to work in greater generality because it applies to many other situations. But if you're interested only in vector spaces, even then you need to know something about modules, because when you have an endomorphism of the vector space, then that pair consisting of your vector space and the endomorphism can be viewed as a module over the polynomial ring. And there, it's not a vector space. I mean, it's a module over a ring. It's not, the polynomial ring is not a field. So that's why this greater generality is useful, even if you are interested purely in talking about vector spaces. Okay, so let's come to today's thing. So the first definition is that of an idempotent. That's an element of a ring whose square is equal to itself. E is an idempotent if E squared is equal to E. When that ring happens to be the ring of endomorphisms of an A module, where A is another ring, and you take the ring of endomorphisms of an A module, an idempotent in that ring is called a projector. Okay, so usually 0 and 1 are, of course, projectors in every ring, and some rings have more projectors, some rings don't have, depends upon the ring. So if you have a family of projectors in the ring, we are going to say that they are orthogonal if E iota times E mu is equal to 0 whenever iota and mu are different indices. Okay, so they're mutually perpendicular or orthogonal to each other. Now here is a proposition. It says that if I have an orthogonal family of projectors, and if every x can be written as so another way of saying this thing here is, I look at the images of these E iotas. These E iotas are, after all, endomorphisms of some A module E. I look at the images, and if the whole module E is the direct sum of these E iota E's, then not the direct sum, it's simply internal sum of the images of these projectors, then it's actually a direct sum. If it is an internal sum, and if the projectors are orthogonal to each other, then the sum is direct. That is what this proposition is saying. So, as I said, the hypothesis that it's an internal sum amounts to saying that this mapping S iota, not S iota, Si, this mapping Si from the direct sum to E is surjective. There's a second part of the hypothesis. Okay. The first part is that these projectors are orthogonal to each other. Let's use that now to show that Si is actually injective. So if we show both these, if we show that it's injective, then it's going to be bijective and therefore an isomorphism, and therefore the sum is going to be direct. How do we show that it's injective? Using the fact that these projectors are orthogonal. So you take something which is in the kernel. Take some element here. It's going to look like E iota of X iota for iota in I, such that the sum is equal to 0. Now choose some kappa in I and apply E kappa to both sides of this equation. On the left, we apply E kappa to the sum. E kappa is linear, so I can, it's going to be the sum of E kappas of these various things, but E kappa, E iota is 0 if kappa is different from iota. That's given to me because they are orthogonal projectors. So the only thing which will remain is E kappa X kappa. Now E kappa is E kappa. That's the definition of a projector, right? The square is equal to itself. So I get E kappa X kappa. Whereas on the right hand side, I get 0. So each of the components is 0, and therefore the mapping is injective. So this proves the proposition. Now let's come to this. When you're given just one projector in an A module E, so it's an endomorphism whose square is equal to itself, then I'm claiming that E is the direct sum of these two modules, the image of little e and the kernel of little e. Okay. So what do we need to show in order to say that E is the direct sum of these two submodules? We need to show that their intersection is trivial and that their sum is equal to E. So, but how do we do that? Another way of doing it is to find a projector F which is orthogonal to E. So that's what it means. EF is 0 and FE is equal to 0. That's what it means for F to be orthogonal to E. And such that E is the image of little e and the image of little f. And finally, to show that the image of little f is the same as the kernel of E. Then in this equation, I'll write this image, replace image of f by kernel of E, and I'll get E as a direct sum of image of E and the kernel of f, which is what is being claimed. Okay, so I have to find a projector F with these properties. Okay, in fact, we can take F to be 1 minus E. That is certainly an endomorphism of the module E. Let us check that it's a projector. I have to compute F squared. Is there some, is there some, there's some noise. Anyway. So let me check that F is a projector. What is F squared? It's 1 minus E squared, which I can expand as 1 minus 2E plus E squared, which is 1 minus 2E plus E, because E squared is actually equal to E. And that's equal to 1 minus E, which is F. So F squared is equal to F, right? That's what it means for F to be a projector. Now let's check that F and E are orthogonal to each other. So let's compute EF. EF is E times 1 minus E, which is E minus E squared. But E squared is equal to E, so that becomes E minus E, which is 0. Similarly, F times E is 1 minus E times E, which is E minus E squared. But E squared is equal to E, so that becomes E minus E, which is 0. So E and F are orthogonal. And the final thing I have to check is that E is the sum of the image of E and the image of 1 minus E. That's clear because every X in E can be written as E of X, which is in the image of E, plus 1 minus E of X, which is in the image of 1 minus E. Okay. And the final thing to check is that the image of F is equal to the kernel of E. So there are two things involved, that the image of F contains the kernel and is contained in the kernel. So these two things are checked here. All is the fact that, could you switch off your mic, please? I mean, the other people who are not speaking right now are requested to switch off their mics so that there's no noise here, right? Okay, so we have proved this, and that was what I wanted to do the last time. I'm now going to, how do I do this? Yeah, I'm now going to open another file, which is here. There it is. Can you see the new file now? Page 31. Yes?
Yes.
Okay, perfect. So this introduces the concept of supplementary submodules and direct summons. So when you have two submodules M and N in a module E, they're going to be called supplementary if E is the direct sum of M and N. As we have seen, this is the same as saying that M plus N is equal to E and M intersection N is 0. So here's a small proposition. M and N are supplementary in E if and only if the restriction to M of the projection from, so the restriction to M of the projection from E to E modulo N is an isomorphism. Okay? So why are these two things equivalent? Okay. Because being supplementary means that M plus N is equal to E and M intersection N is equal to 0. The first thing is equivalent to this map, the restriction of pi to M being surjective, and the second thing is equivalent to the restriction of pi to M being injective. Okay, so this proposition is clear. Now you have this definition of a direct summand, and a submodule M is called a direct summand of an A module E of the ambient module if M has a supplement. Okay, so this is really a condition. It's not as if every submodule has a supplement, right? I mean, you can take the Z module Z, and inside it you can take the submodule 2Z. It doesn't have any supplement. Z cannot be written as 2Z direct sum something else, right? So supplements or sometimes exist, sometimes don't exist. And when they exist, we say that M is a direct summand. If they don't exist, we say that it's not a direct summand. And here's a small proposition. It says that M is a direct summand of E if and only if there's a projector, of course in the endomorphism ring of the module E, such that M is either the image of that projector or the kernel of that projector. And this requires no proof because that's exactly what we have been discussing a couple of minutes ago, right? Because if M is a direct summand, then you can write it as the direct sum of two things and you take the projection. And if there's a projector, its image is of course a direct summand, etc. We have seen this already. Now there's this notion of a split short exact sequence, right? A short exact sequence, recall, is something which is, of the kind 0 goes to E, goes to F, goes to G, goes to 0. That's a short exact sequence. Now, before I can introduce this notion of a short exact sequence being split, I need to recall the notion of a linear retraction and a linear section. So that makes sense for any A-linear map. If little u is an A-linear map from E to F, a linear retraction is a map from F to E such that R composed with U is equal to the identity map of E. The retraction goes from F to E, and when I compose it back with U, or rather when I first apply U and then apply the retraction, I get the identity map of the module E. A linear section is also a map from F to E, A-linear, but here I have to apply first this map F and then the map U, and if I get the identity map of F then I call it a linear section, right? So sometimes you can, maybe this R is called a left inverse of U and S can be called a right inverse of U. I mean, you know that maps can have a left inverse without being bijective, right? Or they can have a right inverse. But here, what is required is that this left inverse and the right inverse should be linear maps. That's why we are calling them linear retractions and linear sections. Now let's come to this short exact sequence. It's and I'm saying that these three conditions are equivalent. What are the three conditions? First of all, this f of E is a submodule of f, right? It's this map f is actually injected. So the first condition is that the submodule f of E is a direct summand of f. The second condition is that this little f admits a linear retraction R. The third condition is that G admits a linear section S. Okay, so we are claiming that these three conditions are equivalent. Okay, so let's prove that 1 implies 2. So if f is a direct summand, that's what we are given, then we know that there's a projector little e such that the image of this projector is equal to this submodule f of E. And we are looking for a retraction. This says that take R to be this retraction. You apply your projector and then take the inclusion of, not inclusion, the isomorphism of f of E with E. E is, little f is an isomorphism of E with f of E because it's an injective map. So it has an inverse, this isomorphism, take the inverse of that isomorphism, right? And you can check that this R is a linear retraction. So 1 implies 2. How about 2 implies 1? So now we are given a linear retraction, little r. I'm claiming that you can take E to be F composed with R. That's going to be a projector. To check that, you'll compute E squared. That's F composed with R, composed with F composed with R. But in the middle, R composed with F is the identity map of E. That's what it means for R to be a linear retraction or a retraction, without even being linear. Anyway, so this identity map of E can be sort of cancelled, and what remains is F composed with R, which is E by definition. So E is a projector, and it can be checked that the image of E is equal to the image of F. So let's come to 1 implies 3. Here we are given that f of E is a direct summand, so it has a supplement E prime. You restrict your map G to E prime, that's going to be an isomorphism. And you can take S to be the composite. G to E prime, that's the opposite, the reciprocal of this isomorphism. And then the inclusion of E prime in F. This S can be checked to be a linear section. For 3 implies 1, we are given a linear section S, and we are looking for a projector. I claim that E, which is S composed with G, is such a projector because its square is S composed with G, composed with S composed with G, but G composed with S in the middle here is the identity map of G. So this whole thing is just S composed with G, which is equal to E. And one checks that the kernel of this map is equal to f of E. And therefore, f of E is a direct summand of the module F. Okay. Maybe I stop here for a few minutes to see if there is any question. Where is my, here it is. Yes, are there any questions? Hello? Okay, so there are no questions. I can continue. now there's this very important concept of a simple A module. So it's an A module E, and we say that simple if sorry? Yes? Somebody has a question? Okay, so E is going to be called simple if it's not 0. And there are no submodules of E apart from, of course, 0 and E itself. Okay? So that it is simple in the sense that it's not made up of smaller things. And the precise definition is that the only submodules are 0 and E, and they are distinct. So if you take Z mod NZ, for example, when is it a simple Z module? You can check that that's the case precisely when this N is a prime number. Okay? So that's one easy example of a simple module. Now here is a small lemma which I've stated here because I'll need it in the proof of the next theorem. It says that if I have a module capital N and two submodules M and N prime, such that M is simple and N modulo N prime is simple, and M is not contained in N prime. Okay. The claim is that then M and N prime are supplementary submodules of N. So for that, what do I need to show? I need to show that their intersection is 0, M intersection N prime is 0, and M plus N prime is equal to N. That's what it means for them to be supplementary in N. Excuse me. So M intersection N, this is certainly a submodule of M, and it is distinct from M. Why is it distinct from M? Because M is not contained in N prime. And therefore, this has to be 0 because the only submodules of M, distinct from M is a simple module, right? So the only submodules are M itself and 0. Similarly, if I look at M plus N prime modulo N prime, it's a submodule of N modulo N prime, but N modulo N prime is simple. And this module is distinct from 0. That's what is given to me. And therefore, this module has to be equal to N modulo N prime, which translates as saying that M plus N prime is equal to N. So that proves this little lemma. Okay. So let's come to this, excuse me, this notion of a composition series. What is that? So I'm given an A module E. A composition series of length R is a sequence of submodules of E. So the first submodule is F0, and it should be equal to 0. The second one is F1, the third one is F2, etc., up to Fr, which should be equal to the whole of E. So it's a sequence, increasing sequence of submodules. And the requirement is that the successive quotients, Fi modulo Fi minus 1, should be a simple A module. That's when I call this series a composition series. So this basically is an increasing sequence of submodules. The first one is 0, the last one is the whole of E, and each successive quotient is a simple A module. Here is an example of a composition series. You take A to be the ring Z and E to be Z modulo P squared Z, where P is a prime. Now this has a submodule Pz modulo P squared Z. So if I take the first module to be 0, the second, F0 to be 0, F1 to be Pz modulo P squared Z, and F2 to be the whole of Z modulo P squared Z, then this series, of course, it's an increasing series of submodules, but it's a composition series because the successive quotients are Z modulo Pz and again Z modulo Pz, which is a simple module. Similarly, if E were Z modulo PQZ, where P and Q are distinct primes, then I have two composition series. 0 going to Pz modulo PQZ, going to the whole of Z modulo PQZ. Here the successive quotients are Z modulo QZ first, and then Z modulo Pz. And the other composition series is 0 containing QZ modulo PQZ, containing the whole of Z modulo PQZ. Here the successive quotients are Z modulo Pz first and Z modulo QZ second. So these composition series are distinct, but what you notice is that the quotients are really the same up to the order in which they appear. Okay, that will be a consequence in general of the Jordan-Holder theorem, which we are going to prove next. But let me just remark that not every module has a composition series. For example, this Z module Z has no composition series. Okay? Because one of the reasons is that it doesn't have a simple submodule. We know what the submodules of Z are. They are all isomorphic to Z itself. And, well, in a composition series, the first one is, of course, 0, but the second module has to be a simple module because that module, modulo 0, has to be simple, right? So Z doesn't have a composition series. But some modules have two different composition series, as we saw here. Now, this Jordan-Holder theorem, Jordan, maybe I should say, but let's pronounce it Jordan as everybody. This says that if I have two different composition series, this F series and this G series, right? F naught F1 up to FR and G naught G1 up to GS. If these are both composition series for the same A module E, then their lengths are the same. This little r is equal to this little s. R is equal to s. And there's a permutation such that the successive quotients of the first one are isomorphic to the successive quotients of the second one. Meaning the successive quotients are really the same up to the order in which they appear. You know, a bit like prime factorization of natural numbers. If I factor a natural number into prime powers and Dr. Gupta does it on her own, then we are going to get the same prime powers up to the order in which we write them. That is going to be the only difference, right? So this is the Jordan-Holder theorem. Now, let me try to at least indicate a proof. It fits in one page. Yeah. Okay, so let's go through the proof. The first remark is that if R is 0, if the length of the composition series is 0 or 1, then of course the theorem is true. No? If the length is 0, then the module itself is 0, and the length is 1, then the module itself is simple. So every other composition series is what you expect it to be. So let's proceed by induction on R, the length of the first composition series. And let's take A to the smallest index. It's going to be between 1 and S, such that F1 is containing G of A. This F1 is a submodule of E, and the G's are an increasing sequence of submodules of E, and G of S is the whole of E. So F1 has to be is certainly contained in G of S. Maybe it's contained in G of S minus 1. Maybe it's contained.
Excuse me, sir. Sir, when R equal to 0 or R equal to 1, how can we prove R equal to S in that case?
If R is equal to 0, then what it means is that the module itself is the 0 module. If the composition series has length 0, then actually there's nothing in it. It's just F0 equal to 0, and it's also equal to the whole module. You see, similarly, if R is equal to 1, it means that F0 is 0 and F1 is equal to the whole module, and F1 modulo F0 has to be simple because it's a composition series. So your module is simple. Now a simple module can
then R equal S will be 1, right?
Then S will be 1, because the only submodules that a simple module has are 0 and itself, right? So that any other composition series will be just 0 the first term and the whole module the second term. So S is going to be 1, right? So if R is 1, then S is 1. If R is 0, then S is 0, etc. And this
thank you, sir. Thank you.
Right, okay. So as I was saying, in general, we are proceeding by induction on R. So this F1, I have these two composition series now of length R and length S. And this F1 is going to be contained in some GA, but not in GA minus 1. There has to be a unique A between 1 and S, such that F1 is contained in GA, but not in GA minus 1. Okay, now let's look at these two submodules, F1 and GA minus 1 of GA. F1 is simple. Why? Because F1 modulo 0 is simple, and F1 modulo 0 is, of course, F1. And GA modulo GA minus 1 is also simple, because this G is a composition series. The successive quotients are simple. And F1 is not contained in GA minus 1. And that's how this little a is defined. It's the smallest a such that F1 is contained in GA. So now these three conditions are exactly the conditions of my lemma on my previous slides, which was there on page 34. And that lemma said that if these three conditions are met, then F1 and GA minus 1 have to be supplementary submodules in GA. Okay? So another way of saying it, a consequence of this is that GA minus 1 is going to be isomorphic to GA modulo F1. And this GA modulo F1 is, of course, a submodule of GA plus 1 modulo F1, because GA is a submodule of GA plus 1. And the other thing which is to be noted here is that F1 is going to be isomorphic to GA modulo GA minus 1. Okay? Both these are consequences of the fact that GA and GA minus 1 are supplementary submodules in GA. Now, what I'm doing is, I had these two composition series, right? The F's and the G's. But from them, I'm going to construct two new composition series, but not for the module E, but for the module E prime, which is E modulo F1. Take E prime to be E modulo F1, or FR modulo F1, because FR is actually equal to E. And the composition series for E prime, the first one is F1 modulo F1, which is 0, because every composition series starts with 0. The second thing is F2 modulo F1, etc., etc. And the last term is FR modulo F1, which is the whole of E prime. The length of this composition series is, you should check that it's a composition series, which is to say that the successive quotients are simple, and the successive quotients are here on the right. They are Fi modulo F1, modulo Fi minus 1 modulo F1, but that's the same as Fi modulo Fi minus 1, which are known to be simple. So now I have a composition series for a different module E prime, but the length of the series is R minus 1. That's my first composition series. And the second composition series is just G naught up to GA minus 1. But GA minus 1, remember, it was equal to, we had identified it with GA modulo F1. And then the next term is GA plus 1 modulo F1, and so on, up to GS modulo F1. But GS is the whole of E, and therefore GS modulo F1 is E prime. E prime was defined as E modulo F1. Well, okay. The length of this series is obviously S minus 1. And this is also a composition series because the successive quotients in the first half up to E minus 1, A minus 1, they are the same as the previous, the successive quotients of the previous composition series of 2, of the composition series 2. Here, this red 2, 2 prime. We are looking at 2 prime. But here we have to check in the second half, we have to check that the successive quotients are simple, but that they are simple again because of this kind of isomorphism which we have with the successive quotients of the composition series number 2. Now 1 prime and 2 prime are 2 different composition series for the same A module E prime. Their lengths are R minus 1 and R minus S minus 1. By the induction hypothesis, this R minus 1 has to be equal to S minus 1, which proves that R is equal to S. And also by the induction hypothesis, the successive quotients of the series 1 prime are the same as the successive quotients of the series 2 prime up to a permutation. Okay. Now, what are the successive quotients? Or they are called composition factors. What are the composition factors of the series 1? They are the composition factors of the series 1 prime and F1, because F1 is the only one which gets omitted when you construct F1 prime from 1. Similarly, the composition factors of the series 2 are the same as the composition factors of the series 2 prime, plus this GA modulo GA minus 1, which is missing here. GA modulo GA minus 1 is missing. But this F1, which was missing in the first one, and GA modulo GA minus 1, which is missing in the second one, are really isomorphic to each other. That's what we had proved, right? So when you include F1 in the first one and GA modulo GA minus 1 in the second one, you again, up to permutation, you get the same composition factors. So that proves the Jordan-Holder theorem. It's a very basic fact. I mean, we have proved it for modules, but it's also true for groups, I mean, which are not necessarily commutative. And it's even true for what are called groups with operators. So groups with operators are those in which you have some auxiliary set and some endomorphisms of the group are given. But let's forget about that generality. We just need it for this commutative case, the case of modules. And let's go on. Okay, so I have very little time left. We come to modules of finite length. So we will say that an A module E has finite length if it has a composition series. We have seen that any 2 composition series for the same module have the same length. So we can define the length of this module to be the length of any of the composition series for that module. So to say that the length of a module is 0 is the same as saying that the module itself is 0. To say that a module has length 1 is the same as saying that the module is simple. Okay? Now here is a proposition. It says that if I have an A module and as a module M, then this E has finite length if and only if M and E modulo M both have finite length. And if such is the case, then the length of E is actually the sum of the length of M and the length of E modulo N. So how do I prove this? Let me prove that if M and E modulo M have finite length, then E has finite length, and the length is actually the sum of the lengths of M and E modulo N. Okay, so by hypothesis, M has a composition series M0 up to MR, and E modulo M also has a composition series, N0 to NS. Using these two things, I can cook up a composition series for E, of which the first R+1 terms are the composition series for M. And the term after that is pi inverse of N1, where pi is the projection from E to E modulo M. Here it is written in green. Pi is the projection from E to E modulo M. N1 is this, I'm not looking at N0, which is 0, and pi inverse of N0 is actually M. But that's the same as MR, right? MR is equal to M. So I don't want pi inverse of N0, but from pi inverse of N1 onwards, I write down these terms. Pi inverse of N1 up to pi inverse of NS. So this is certainly a series of length R plus S. Is it a composition series? In other words, are the successive quotients, the so-called composition factors, are they simple? Now, for the first half, it's clear because they're given to be simple. Mi modulo Mi minus 1 is a simple module for every I that's given to you. How about these things? So here as well, essentially that's given to you because the quotients here in the second part are going to be the same as the quotients in this composition series for E modulo M. So this thing of length R plus S is actually a composition series for E, and therefore E has finite length, and that length is the sum of the length of M and the length of E modulo M. Let's prove it the other way. If E has finite length, then so do M and E modulo M. That's what we need to prove. So we are given a composition series F0 up to Fn for E. So F0 is 0, Fn is equal to E, and all that these successive quotients are simple. Now I can intersect each of these terms with M. F0 modulo intersection M is certainly going to be 0, and Fn intersection M is certainly going to be M. And these intermediate things, they are, of course, submodules of M, but all these these inclusions don't need to be strict. They might be equalities. If you remove all the equalities, then what you will get is a composition series for M. Similarly, I can take the images of these submodules under pi. The pi is this map from E to E modulo M, the projection. So when I take the images of these modules, pi of F0, that's of course 0, pi of Fn, that's of course the whole of E modulo M, and then there are these intermediate things, they're all submodules of E modulo M. But again, the inclusions here need not be strict. They might be equalities. So if I suppress all these terms in which equality occurs, then I get a composition series for E modulo M. And therefore, M and E modulo M also have finite length if E has finite length. Of course, if they are finite length, then the sum of their lengths is equal to the length of E, which we have already proved that. Okay, so we have proved a special case of this proposition. Here, what is the proposition? It says that if I have an exact sequence, 0 to m0 to m1 and so on, all the way up to m little n to 0. So it's not necessarily a short exact sequence, right? It's an exact sequence of some length n. And if each of the modules has finite length, then the alternating sum of their lengths is equal to 0. This is the claim. And this is obvious. If n is equal to 1, n is equal to 1 means that you have a map U0, and then which is injective and surjective. And so these two modules will have actually, they'll be the same module or isomorphic modules. So they'll have the same length, and the difference of those lengths is of course going to be 0. So that's completely obvious for n equal to 1. What happens for n equal to 2? For n equal to 2, you get a short exact sequence. You get a short exact sequence like the one here. I didn't write it as a short exact sequence, but m is a submodule and the quotient is E modulo m. So 0 to m to E modulo m, that's a short exact sequence of length 2. I mean, n equal to 2 here. And we have proved it for this case, n equal to 2. So let's use induction on n. By induction, so how do you use induction? The idea is to split this sequence of length n into two sequences, one of length n minus 2 and the other of length 2. How do you do it? You look at the map un minus 2. It has a certain image. Of course, the map, it's surjective onto its image. So you terminate the sequence there. And then this image is of course contained in mn minus 1. So this is injective. And then the image of un minus 2 is of course equal to the kernel of un minus 1, because this sequence is exact by hypothesis. And this un minus 1 is surjective. That's given to us. So from this sort of exact sequence of length n, I get two exact sequences, one of length n minus 2 and the, I would call it length n minus 1 perhaps. Yeah, and the other of length 2. Okay? By what we have proved already, for the second one, which is a short exact sequence, we have this relation. The length of the middle term is equal to the sum of the lengths of the sub and the quotient. By induction hypothesis, this sequence of length n minus 1, the alternating sum of the lengths of these modules has to be 0. So when I put these two equations together, I get what is required. Okay? So this is a very simple proof. I don't know whether you have seen something similar, which is the following. So instead of taking this exact sequence of A modules for something A, let's take an exact sequence of finite commutative groups. Okay? And now you try to prove that the alternating product, it's not sum this time, it's the alternating product of their orders is equal to 1. That's what you need to prove as an exercise. Okay? So, for example, in a short exact sequence, you know that the order of a group is equal to, finite commutative, in this case commutative, but doesn't commutativity is not required. The order of a group is, of course, equal to the product of the order of a normal subgroup times the order of the quotient. Okay. So now suppose I have an A module E and two submodules M and N. And these two submodules are of finite length. This module E itself may or may not have finite length. I'm making no hypothesis. But what I'm claiming is that if M and N have finite length, then M plus N and M intersection N both have finite length, and the length of M intersection N plus the length of M plus N is equal to the length of M plus the length of N. Okay? How do we prove this? Okay, so the first remark to be made is that the length of M direct sum N is of course equal to the length of M plus the length of N. You know, because you have this exact sequence. M going to direct sum of M and N going to N. So what the length of the middle thing is the sum of the lengths of the sub and the quotient. And M plus N is a quotient of M direct sum N. We have seen that if a module has finite length, then every quotient also has finite length. So M plus N has finite length. How about M intersection N? It too has finite length because it's a submodule of M. Every submodule of a module of finite length has finite length. This we have already seen, right? We have seen it here. Okay, so we have proved that these two modules, M intersection N and M plus N, have finite length. But we have also proved that this sequence here is exact. M intersection N going to M direct sum N going to M plus N. The first map is sort of the diagonal map, and the second map is, I'd call it P minus Q, where P is the projection onto M and Q is the projection onto N. So, because of this exact sequence, the length of M direct sum N is going to be equal to the length of M intersection N plus the length of M plus N. But I had already computed the length of M direct sum N as the length of M plus the length of N. So I get this thing, which is what was to be proved, right? And similarly, we had this other exact sequence written in green here. So this allows us to prove in exactly the same fashion that if I have two submodules M, N of an A module E, and if E modulo M and E modulo N have finite lengths, then E modulo M intersection N and E modulo M plus N also have finite lengths, and you have this relation between the lengths. I've written little l for length, but this relation follows exactly as before from this short exact sequence. Okay, so now we come to a very important concept, and I have maybe only 3 minutes to explain it, but I'll take a little more time, maybe only 5 minutes. So this is the concept of a free module. So what is a free module? Recall that when you have a family of A modules, you can take the direct sum. Okay? When each of these modules is the same as the ring A itself, then I don't know whether I had introduced this notation, but then the direct sum is called A to the power I, but with the I is within brackets. So it's not all mappings from I to A, it's all mappings with finite support. and so that's here it's written down, and this is called the free module on the set, free A module on the set I. And you are actually a map from I into this free A module, sending E kappa to the family X iota, where X kappa is equal to 1 and X iota is 0 for every iota different from kappa. Okay? So that's the mapping E from I to A to the power I. Okay, kappa going to E kappa. Now, this construction, the free module on the set I, along with the mapping from I into that free module, has a certain universal property. What is that? It says that if I'm given any other pair consisting of an A module E and a mapping F from I into E, then there's a unique A linear mapping. Of course, this mapping little f is not A linear or anything, because I is not a module, it's just a set. But this little g is an A linear mapping from this free module to E, such that f is equal to g composed with E. Here is the diagram in red. I is given to me, and I construct A to the I, which is the free module on I, and it comes with a mapping from I into mapping E from I into A to the I. Given any other module E and a mapping F from I to E, there's a unique mapping little g from A to the I into E, which makes this triangle commute. Okay, so this is more or less, it follows from the construction, the definitions, and this. But the important thing is to remember to understand what is being asserted. So that's the defining property, more or less, of free modules. So that leads to the concept of free families and bases in a module. So if I'm given a family of elements in some A module E, we have seen that to say that this family generates E is the same as saying that this mapping from A to the I to E, which sends E iota to X iota, right? By the universal property of the free module, there's a unique mapping phi which takes E iota to X iota, and it's A linear. So if this mapping is surjective, that is the same as saying that this family generates the A module E. So the notion of a free family is that this mapping phi should be injective. And the notion of a basis is that this mapping phi should be bijective. Okay? So in general, I mean, if I'm given a mapping, if I'm given an A module E and a family of elements X iota in E, I get, where the iota is in some indexing set I get an A linear mapping from A to the I, from the free module on I to E, sending the E iotas to X iotas. If this mapping is surjective, this family generates the module. If it's injective, we say that the family is free. If it's bijective, we say that the family is a basis. So these are very important concepts. So, and an A module is called free if it has a basis. If there is some family of elements of that module which form a basis in this sense. I've just defined what it means for a family of elements in a module to be a basis, or a free family, or a generating family. A basis is both a free family and a generating family. Okay, so the A module A, of course, is free. The element 1 here is a basis. the Z modulo NZ is not free for any n. The Z modulo Z is of course free, but Z modulo NZ is not free. You can, okay. The Z modulo Z is free, but doesn't have a unique basis. 1 is a basis, and so is -1, right? So what does this proposition say? Says that if I have two A modules, E and F, and I have a basis of the first module, E, and a family of elements of the second module, F, indexed by the same set I, then there's a unique A linear mapping from E to F, which takes B iota to C iota for every iota. And this is more or less easy consequence of the universal property of free modules. Now, this is what we have discussed here. Okay. So, here is a small proposition which says that if I'm given a family of elements of an A module, this family is free if and only if every finite subfamily is free. Okay? This comes from the fact that, basically this, the direct sum of a family of modules, each element has only finitely many components which are different from 0. Okay? So basically that's what it amounts to. And here is something which is worth remembering, that every A module E can be written as a quotient of a free A module. Okay, how do I do it? Of course, every A module has a generating family. For example, I could take S to be equal to E itself. Then, of course, there's no doubt that E gets generated by S. So then, and I look at the unique A linear mapping from A to the S to E, which takes ES to S. This is obviously surjective, so E can be viewed as a quotient of A to the S, but A to the S is, by definition, a free module. It's free on the set S. So every A module is a quotient of a free A module, okay? And I have only 2 more slides, so I'll just take 2 more minutes. This one says that, if I have a short exact sequence, A, B, C, in which C is free, then such a short exact sequence always splits. I don't know whether I remember, you introduced this terminology to say that a short exact sequence splits means that this little f has a linear retraction, or equivalently, that this little g has a linear section. We had proved the equivalence of these things earlier. Why does this hold? Why does a short exact sequence in which C is free always split? It splits because I can take a basis of C and I can take a family of elements in B which map to that basis. Then there's a unique linear map from C to B which takes that basis to those chosen elements, and that is a linear retraction of G. Okay? And the last thing I want to mention is this very curious fact that if an A module, by the way, of course, it should be obvious that some modules have bases and some don't have bases, right? And some might have finite bases and some have infinite bases. So what this proposition says is that if E has 2 bases, if it has 1 infinite basis, then every other basis of E is also infinite and actually equipotent to the basis B. And here's a small proof. So it says that by symmetry, it's enough to prove that if I have a generating family S, then it has at least as many elements. Its cardinality is at least that of the basis B. And here is how you prove it. It's well, it's more or less straightforward. So I leave it to you for your own. You can read it on your own, and let's finish the session today by asking if people have any questions.
Sir,
Yes.
if a module has a finite basis,
Yeah.
B,
Yeah.
then if every other basis has the same number of elements that basis, that is number of elements in that basis will be same or not?
Okay, so that works for vector spaces. If if your ring A is actually a field, then it's true. Unfortunately, and it also works for commutative rings. Okay, if your ring is commutative, then that's true. Unfortunately, if the ring is not commutative, or I should say there are rings which are not commutative, of course, for which this is not true. For which
So generally we can say
in
about the
general,
dimension.
it's not true. But the more interesting cases are the ones in which your ring is a field or it's commutative. In both these cases, it's true that if you have a finite basis, then any other basis will also be finite and will have the same number of elements.
Okay, yes. Then the dimension will be the number of elements in that basis.
You
right?
could define the dimension to be that, yes. Yeah.
Okay,
that's right.
Thank you, sir.
It's sometimes called the rank. If it's a vector space, if you are working over a field, then it's called the dimension. But if you are working over an arbitrary ring, sometimes it's called the rank of the free module.
Okay.
Yeah.
Okay.
Right.
Thank you, sir.
Right. Other questions? Yeah. I see that people are very assiduous. There are so many of them who are present. Yeah, Dr. Gupta, are there any questions from, yes?
No, sir.
Yeah. Oh, so does everybody have access to the slides, the notes?
Yes, sir.
Okay, very good.
So we provide the slides too in the Google Classroom.
Right. You can also provide those written notes which are more detailed, right? That PDF file I sent you.
Yes, I have.
So you can also make it available to the students. It's much more detailed and contains many examples and many of the things which I could not cover in these lectures because time is limited. So
okay, I will send.
You can take a look at that set of notes as well.
Okay.
Right. Okay.
So claps for Professor Dalawat. Thank you so much, sir.
Yeah.
Thank you, sir.
So next we will meet on Friday.
That's right.
At 5 p.m.
Okay.
With Professor Dalawat.
Right.
Thank you so much, sir.
Okay. Bye.
Thank you, sir.